Hello, everyone. I know some of you might be finishing up your lunch, but I want to keep keep us on the clock. So it is now time for us to begin the second block of our Science of the Poles virtual workshop. During the second block, we're going to be focusing on the photosphere and the polar fields. For our scene setter for this block, we have Anthony Yeates, who will be giving us a rundown of everything we should know about the photosphere and the polar fields. Anthony, do you want to go ahead and start sharing your slides?
Yep, okay. Can you hear me okay?
I can. Take it away.
Excellent. Okay, I just need to try and play this. Great, so you should be able to see the slides. I don't think I'm going to tell you everything about the photosphere, certainly, and not very much about the polar fields. But what I thought I would first of all do is define what we mean by the polar field. And I found a nice definition from Gordon Petrie that the polar fields are basically the large-scale unipolar magnetic fields that you typically see near the heliographic poles on the sun, so the North and South Pole, and something like above about 60 degrees latitude or 70 degrees in each hemisphere. Now, they have opposite polarity at the two poles usually, the North and South, except during the polarity reversal when there's no kind of net field necessarily or consistent field at each pole. The actual amount of magnetic flux is not very high. It's less than a major active region, for example. But it's nevertheless important, partly because it's unipolar over quite a large spatial scale, these polar caps, if you like, but also because of the role that the polar fields play in the solar activity cycle that Robert alluded to earlier. So in particular, the fact that the polar field is kind of thought to be a signature of the sun's poloidal field that's then wound up to make the toroidal field of the next cycle. This is one of probably the earliest observation of the polar fields from Babcock and Babcock. I don't know if you can see here, but they have these sort of traces at different latitudes. I don't think I have a pointer, but if you look in the north, you can see the line is kind of the graph is above the horizontal line, indicating one polarity, and then in the south, it's near the South Pole, it's below the line, indicating the opposite polarity. And this was in the 1954. So they observed these large-scale polar fields with what they actually look like if you look with a modern instrument is a little bit different. There's a view from Inode from the Solar Optical Telescope. It's again a magnetogram, and of course it didn't fly over the pole. They've just sort of projected it to make it look as though it did, based on images taken from the ecliptic. But what you see are that the magnetic field is not kind of smooth. What it actually consists of are these kind of localized patches, which they measured have kind of quite strong field strengths, kilogauss flux tubes, if you like. So the field is sort of broken up into these patches, but what they do find is that all of these patches had the same sign, so the same magnetic polarity. So there is an overall kind of larger scale structure there that is masked a bit when you look at high resolution. So if you look at the sort of latitudinal profile, then typically around solar minimum, you find that it's something like cosine to the 8th theta, the magnetic field. So if sine to the 8th of latitude, if you like. And so it's quite concentrated near to the poles in these so-called polar caps. I made a little comparison here. These are just extrapolations of two suns that have the same amount of magnetic flux, but on the left it's just a dipole, cosine theta, and on the right it's this so-called top knot structure where it's pushed towards the pole. And you see it does have an effect on the structure of the coronal field as well, for example, which we'll hear about later. Why is it concentrated like this? Well, we've known for quite a long time, since the work of I think Neil Shealy in 1980s that it's caused by the meridional flow at the surface, which we've been talking about, which flows poleward. This is just two surface flux transport simulations here, with and without meridional flow. So you're looking at the sort of radial magnetic field in a longitude average, if you like, as a function of time against latitude. And you can see that with the meridional flow, you form this concentrated polar cap. Without it, you just get a dipole that will just decay. So you don't then get a kind of steady state, and it doesn't look like the real sun at all. So the meridional flow is important for the polar field. Talking about the sort of time variation, you can sort of ask how far back in time can we actually go with observations. We've only had magnetograms for sort of half a century or so, a bit longer now, but we can actually go back further thanks to a correlation that was noticed also by Neil Shealy, where if you look at what they call white light faculae, so it's kind of bright points at the poles, and you just count the number of those points at any given time, it's actually quite well correlated with the magnetic flux in the polar cap as we measure from magnetograms. And so you can use this relationship to extend back in time because we have white light images for a longer period. And this is what Andres Munoz Jaramillo did here, together with Neil Shealy, who'd obtained these faculae data for a lot of previous cycles. This basically covers most of the 20th century here. And the magnetograms are these kind of multicolored curves that start in about cycle 21 here. But the red and blue show you the north and south polar fields going back in time, polar flux. So what can you see here? Well, you can see obviously that they reverse in sign every solar cycle, but you can also see that the amplitudes vary quite a lot. And so the question is then what generates these fluctuations in amplitudes? And the kind of hypothesis of the community is that these fluctuations from one cycle to the next are caused by fluctuations in the emerging active regions, which are ultimately the source of the magnetic flux at the poles. So it can be fluctuations in the number of active regions, so like the sunspot number, if you like. But more importantly, it can be fluctuations in the properties of the region. So, for example, how close to the equator they are, or how tilted they are. So how much of a north-south component does their field have? So this kind of understanding is based on the flux transport model, as I said. We have several of us were involved in a recent review paper as part of an EC workshop where we sort of talked about our latest understanding of this model in this kind of context. But the basic model is quite simple. You have essentially you treat the radial magnetic field on the photosphere as a passive scalar. So it gets moved around by advection by the large scale flows, such as the meridional flow, and then it's spread out by the kind of action of the convection, which you model with a diffusion term. That's the red one here. The last term, the S, is the source term, because of course you have new regions emerging on the sun. And in most of these models, you just sort of treat this as a superposition of individual active regions that kind of appear instantaneously relative to the length of the solar cycle. This is just showing you an example of one of these regions. You see that because it's near the equator and it's tilted, so one polarity is nearer the equator than the other one. As the flux spreads out by the diffusion, some of it's going to escape into the opposite hemisphere, some of the blue flux here. And then you can see in this time latitude plot that once it's escaped, it gets pushed towards the opposite pole by the meridional flow. And so you end up producing a net polar field at the end of the cycle from this single active region. And it's kind of a steady. Once it gets to the pole, it can't cancel with the opposite pole because it's too far away. And the nice thing about the classical flux transport model, at least, is that it's a linear equation. So if you know the solution for one active region and you have lots of active regions, you can just add them all together, and the solution will be the sum of all the individual solutions. So there's been quite a lot of work done on how does an individual active region evolve, and this is relatively recent, or there's been progress relatively recently, so the last sort of 10 or so years. And in particular, we've learned that what I call here the dipole amplification factor is a Gaussian in latitude. So what I mean by this is that if you take the sort of axial dipole moment of the region when it emerges, and you ask, will this be enhanced by its subsequent evolution or will it decay? Because ultimately this is what's going to produce the polar field, the sort of long-term dipole moment. You find that the kind of amplification factor is actually a Gaussian function of latitude. So where I mean latitude where the bipole originally emerged, or the active region. And Christophe Petrové here has plotted this Gaussian for a variety of sort of earlier flux transport models from the literature. And what you see is that the width of this Gaussian varies quite a lot from one model to the next. That's this lambda r parameter. And this parameter is actually important for the polar field because it basically sets how close to the equator do you have to emerge in order to make any difference to the long-term polar field. Because you need the thing to be amplified, or at least not to decay. And so the width of this Gaussian essentially sets that distance. And so very briefly, something I'm interested in at the moment is what is the actual correct value of this parameter for the real sun, as it were. And I've been trying to do this by doing a longer flux transport model that's quite closely calibrated to the real sun. So we're using, I can tell you more details about this later if people are interested, but I'm using basically sort of digitized Mount Wilson data to try and go back in time with individual active regions because the fluctuations are important and try and fit a flux transport model. And this seems to fit quite well. These black stars here are the observations of polar crown filaments that are just sort of showing you that we are getting roughly the right polar field reversal time and so on. It's actually optimized against the polar fields that I showed you before from Andres. But to cut a long story short, what I'm finding is that this lambda r parameter is actually quite small compared to some of those previous models in the literature. It seems to certainly be less than 10 degrees, somewhere around 6 or 7 probably. So that's quite interesting. It means active regions have to really be quite near the equator to matter. So I'm just going to finish with some sort of open questions that we may or may not want to take up in the discussion. What's interesting to me about this trying to predict the polar field is, so how good is this kind of classical model that we've basically been using, or I've been using? Do its parameters need to vary over time to represent the real sun? So like the radial flow speed or whatever. Should it even be a linear process in the first place? Are there non-linearities in the flows that matter? And I think it would be really interesting to try a similar study in one of these fully advective flux transport models. So something like Lisa's AFT model or the HIP-FT model that predictive science have been using, and see whether that changes the answers to this question. And then there's also this long-standing debate of whether you need a radial decay term or diffusion in to really model what's happening at the poles. Is flux being lost there through kind of three-dimensional processes, if you like, that you're not going to capture in one of these surface models? And then just more broadly to finish, I guess it's kind of interesting to ask how extreme could these variations in the polar field strength get? I mean, could it be that this is somehow these what I mean by rogue regions or active regions that have very abnormal properties that that lead to a strange polar field? Could that be what caused things like the Maunder minimum in the past? We don't know, I think. So these are sort of questions about the polar field, but hopefully there'll be some interesting discussion.
Thank you so much, Anthony. Very nice presentation. We'll open the floor to a couple of questions. I'll start off with one that is in the chat. Shay asks Anthony, can the Gaussian distance be constrained by the fact that we have active longitudes?
Well, yeah. So the question is, can the width of this Gaussian be constrained by the fact that you have active longitudes? I haven't thought about that at all, and I don't immediately see the relation, but that, does Shay want to explain more? I'm not sure.
I mean,
I can't see the chat, by the way, so that's
oh, sorry. Yeah, I always forget that if you know, I have that problem too when you're sharing, you can't see the chat. Yeah, so just the wider, it just occurred to me that the wider curves go up to this lambda distance of like 40 and 50, what I'm assuming is degrees.
yeah.
But we never see active regions. So even though they may not have a strong impact, the fact that we never see them, does that kind of discount those like Gaussians of that width, which would then, of course, impact the strength of the amplification factor?
Yeah, I see what you mean. So I think I can't remember now exactly how this graph is produced. It doesn't necessarily mean there were any regions at that latitude in the model. There probably were in some of these, but so for example, the yellow one, this was based on observed active regions, I think. So, which makes me wonder whether that's actually. I don't think it directly corresponds to. It's some kind of a fit to what this would be for those parameters, if that makes sense.
It makes sense, but also it doesn't make sense that they got data points up to 50 degrees, but it's okay. It's not your
No, I mean, I think it's sort of saying that if an active region did emerge at 50 degrees with those model parameters for the flux transport, then it would decay at whatever rate we have here, basically. Something
we
like
have
that.
another question in the chat, and then we'll take the raised hands. The next question in the chat, Sushant, the SFT model is calibrated to observations without using far side sunspots. Would the inclusion of those change the calibration? If it does, what would that tell us?
So it's calibrated. I'm using maybe I have an extra slide somewhere. So I'm deriving the regions from calcium K, kind of plage regions, essentially. And so we only have synoptic maps, of course, that we only see the front of the sun. So it's certainly true that we're going to be missing some of the regions. What I find, so I can compare my kind of reconstruction with the real magnetograms in the period where we have magnetograms. And you use that to set the amount of magnetic flux. So in some sense, I have calibrated it to synoptic magnetograms. So probably in that sense, it's underestimating flux, but we're not really interested in the sort of absolute amount of flux. We're really interested in the polar field. So I don't know whether that would make any difference if you would sort of make that correction and then allow for it, and it would sort of remove itself, I think.
And presumably those would primarily be the smaller active regions, which would probably not have much of a contribution.
Yeah, I think probably.
Okay, let's go ahead and go to the hands raised in the hands raised. Yiming, I think you had yours raised first. You want to ask a question? Yiming, are you there? Okay, looks like he's lowered his hand. Robert, do you want to ask your question?
I was muted. I'm sorry.
Oh,
is
sorry,
Amy.
go ahead, Yiming.
Okay, the Hinodi observations. Now, in their paper, they compared the polar field, their polar field, with a quiet region at low latitudes. And they said, oh, it's completely different at the poles. But what they should have done is compared their polar field with a unipolar region at low latitudes. And then you find it looks the same. And in other words, the flux is clumped, it's concentrated at the supergranular vertices. And that's also a good way of estimating the polar field strength. You look at a low latitude region, unipolar region at the limb, and compare it with the polar field that you see in the magnetogram. And another brief point is the effect of those rogue regions depends a lot on the meridional flow profile that you adopt.
Yes.
So if the flow is strong at low latitudes, which is what we think, then that's going to limit the effect of the regions, because the flow will, the rogue region will have a big effect if the opposite polarity can diffuse across the equator, and then that separates the two polarities. Then you get strong polar fields. But if the flow sweeps both polarities poleward in the same hemisphere, then the rogue region won't have that much effect.
So I guess I should, so as Yiming said, this delta U parameter at the bottom here is in the kind of denominator. That's essentially how strong the flow is at the equator. So you can see if that's larger, then it's going to be, sorry, what am I saying? The delta U is, it's the divergence of the flow at the equator. So if that's larger relative to the diffusion, then the width is going to be smaller of this thing. But I think it's important that it's relative to the diffusion, and that is kind of problematic observationally, because we can't really, using the model, we can't disentangle the flow and the diffusion, if you see what I mean. Whereas they're observationally very different things. So it's a bit, that's a limitation of the model, that it only really, this kind of analysis only really constrains the ratio of those two things.
Yeah, that's the problem I have with the flux tracking, that to derive the meridional flow profile, because it doesn't separate the diffusion, the supergranular diffusion, and the meridional flow.
Yeah.
All right, Robert, you were next.
Yeah, so before I ask my question, I just want to comment on the previous question. So if this becomes narrower and more peaked, the rogue active regions become more important, not less important. So you've got two competing effects. You've got the gradient of the large scale field set up by Joyce's law, and this extends over a wide range of latitudes. But these curves mean, especially if it's more strongly peaked, you're only sensitive to the emergences to this gradient right near the equator. And then the ephemeral regions become more important. Not the ephemeral regions, the rogue active regions. So the more sharply peaked you are, the more important the rogue active regions become, not less important. My question was to do with this nesting again. So active longitudes, but I think nesting is probably more accurate. As soon as you begin having active regions preferentially occurring where there's previous active regions, they will see the large-scale inflows into those active regions, and they will affect them. And then I think this is an important point. It means the linear part of the model is no longer justified, and it means some of the inferences are perhaps questionable. No? Or...
Yeah, no, I think that's true. I want to try and do a version with a model for the inflows and see if it makes any difference, at least for my calculation.
Yeah, I agree.
The problem is you then have another parameter to play with, so whether we can still constrain it enough, I don't know.
Okay. Yang Lu is next in the chat. He says, would the inflow in active regions affect the polar field evolution? Which I guess is reiterating the previous conversation. I don't know if you want to comment on that any further, Anthony?
So the only thing I would say about that is I think in some sense, when I optimize the meridional flow against observations, it'll be on an average taken into account. So, like if there were inflows present, then, and you included that in the model, you would change what the meridional flow was optimally in the model. And so the question is, would it be a better fit to the observed kind of butterfly diagram or not? I don't really, and it might be quite hard to tell, is my guess, but they certainly have an effect, but they're kind of taken into account, at least in an average way, even in the basic model.
All right, thank you so much, Anthony, for setting the scene for us. We're now going to move to our lightning talks. And again, we'll hold the questions until after all of the lightning talks are done. We're going to start off with Dean Pesnell. Dean, do you want to share your slides?
Okay.
Go right ahead.
Okay, I'm going to talk a little bit about our work on polar faculae, and in particular, we're going to emphasize some early results from the polar magnetic field that we see in those faculae. And some people have spoken about faculae already, so here's an example. One of our first detection techniques was to do streakograms, where we look at a day's worth of images. And can you see my cursor?
Yes.
Okay, so these streaks here, these are polar faculae, and we were able to actually measure the lifetime of the faculae quite well using this. For instance, this faculae down here lasted somewhere on the order of 2 to 3 hours, because it only shows up in 2 images of the AIA 4500. We've now counted faculae between 2010 and 2022 in HMI IC images that have had limb darkening removed. This is very similar to what Andres did with the MDI measurements. But what I would like to talk about today is the average magnetic field of these faculae. Now, we assume, based on what you saw from Hinode, that the large magnetic fields we see in the faculae mean that they're pretty much the total contribution to the field in the polar regions. And so we don't have to go and measure the field at all points. We just have to measure the field where the faculae are. So we use the identified faculae to go in and extract the vector magnetic field from the HMI data. And for this example, we're just going to plot histograms that are then smoothed into kernel density estimates of the various components of that field. So here's the radially outward polar field. And you can see that we have, in 2010, we have the oppositely signed fields. And then as the solar cycle 24 progresses, the negative decreases and the positive increases, and reaches a rough constant, as can be seen at around a little over 200 Gauss here. And the south has the opposite behavior. Now, what we think is interesting in here is that we do see a continued small, but almost always fields of the opposite sign. And we saw this in the streakogram analysis when we looked at the field using those identified faculae. So we never really see the radial field become unipolar in these facular magnetic fields. Now, but we actually get to see the theta component, the north-south component of the field as well. That's included in the HMI data. And now you get a little bit more complicated dependence, where it starts off, it indeed does the sign change you expect But here, because we only have 1 month of data per year, we never really get to see a true sign reversal. It happened sometime between March, excuse me, September of 2012 and September 2013. This azimuthal field goes to a 0, and about 2 years later, between March of 2014 and March of 2015, the longitudinal field, or the east-west, or excuse me, the southern hemisphere goes through a 0. But we never really see a nice sign change like we see in the north. But once again, there's still here, even as we go into solar minimum in both cases, there are faculae that have oppositely directed magnetic field. And then what we found was that the longitudinal direction tends to be a bit more of a random variable. It's not, peak it's not a single peak with wings, but it's more distributed around 0 than the ridge plots for the theta and R, which certainly have some kind of a maximum point that you could associate with a true value of the field. And so here we see that the phi component looks to be a bit more of random. It has the same magnitude as the theta field, but it seems to be more randomly oriented in space. So these are as far as we can tell, these are the first time we've been looking at the vector magnetic fields of observed polar faculae over in the optimal viewing period for the poles over more than a solar cycle. We do find that the ratio of the radial field and the azimuthal field is about 5 in the northern hemisphere and about 6 in the south. This is more or less consistent with some of the work that Life has done in the past, but we haven't sat down and really analyzed it to see what difference, whether that is actually the same, but it is consistent with a radially dominated field assumed by WSO. We should recognize this shouldn't be a surprise. That theta component has to go to 0 at the pole, so it's not surprising that it's becoming radially dominated at the pole. The evolution of the polar faculae magnetic field over solar cycle 24 is more complicated than a simple view of the field vanishing at solar maximum. That's a very useful, simple view. We Babcock-Clayton model, and I've used this simple view a lot, but I would take money that solar cycle 25 will look different, because that's just the way the sun is going to be. So I'd like to thank HelioCloud for providing the computational support for this research, and the HMI team for putting the data we used onto HelioCloud. And so that's it.
All right,
Thank you.
thank you so much, Dean. Again, we're going to hold the questions until both our lightning presenters have given their talks, and then we'll circle back. The next lightning presenter is going to be Alejando Moreno Vacas. Alejandro, do you want to go ahead and share your slides? Great.
I'm sharing the slides.
Wonderful. Thank you.
Do you see
Go
them?
ahead. Yes, please go ahead.
Yeah. Okay. Perfect. So, well, good morning, everyone. First, I want to thank the organizer for inviting me to present this work I'm doing with my colleagues present in the slide, and this work I will talk about polar stereoscopic analysis with solar orbiter. Oops. Okay, sorry. Okay, first I want to present briefly the polar SUP, that is the solar orbiter operation plan that we had past October 2023, and it was divided in 2 days, one on the 17th and one on the 31st, which coordinators were Hannah Strecker and Julian Blanco. And in this table, I just summarize briefly the main characteristic of these SUPs. So for us, the important point is the position of solar orbiter. For example, in the 17th, we had colatitude with Earth, and the longitude was near 50 degrees. While on the 31st, the latitude was maximum and the longitude was just a few 20 degrees. On board solar orbiter, we have recording simultaneously the high resolution telescope of Phi and also the high resolution imager of EY. that both recorded during few hours different maps at different cadences. And also in co-observation, we had measurement with the SP. Well, and a part of this, we also have different co-observation with thickest and SPICE. That is, SPICE is also on board Solar Orbiter. And after that, we have data available coming from Solar Orbiter, that is from PHI plus SPICE. And also we have data available from co-observations coming from ground-based or onboard instruments like HMI, AIA, Hinode, or thickest. For us, for this work, it is really important to have the work coordinate system metadata correctly defined, because we are looking from two different viewpoints. That means that we don't have the same field of view, and also the projection effects plays an important role. A part of that, this is the first time we do that. Now we are on the ecliptic plane with Solar Orbiter, and in the future SUPs, we will go higher in latitude. So that means that we need to know this WCS information correctly for the different instruments. Another important parameter for us is the signal to noise ratio, because that will means directly the quality of the data, and it is really important for the future SUP, and we are planning to average different data sets to improve this ratio. And well, as I mentioned before, and in a future SUPs, we will reach higher latitudes and even longer observation that will allow us to make different kind of studies. And it will start more or less on March 2025. Okay, and now I just will present the line of sight magnetic field maps I'm working on. On the right, you have the 50 degrees data set, and on the left, on the left 50 degrees, on the right, the 20 degrees one. Well, I don't know if you have worked sometimes with the data, but if you know the WCS information is a bit a mess, and we have to define it by hand, correct it, and then we used also the 45-second line of sight HMI magnetograms to align both maps. Well, this is the final result. Our work consists now in determining, define the different areas, these small rectangles you see here, and the important point is that they are the same magnetic feature or the same area feature in the sun, and we are sure about that because the WCS information is properly defined. That is the point, because well, you will see in the next example that the projection effects plays an important role. But here, as you can see, the areas are really small because we are close to the pole, but maybe this is not a proper projection to show this data. So we decide to project it to a plane. That is the Carrington map, the Carrington projection. Now we can do it because we can transform it using this WCS thing. And well, this bottom row is the final results we obtain. Now you can see that these areas are really easier to compare. Because this projection allows us to see them properly. Okay, and just to finish, I want to show you one example of these areas that I selected this from the 50 degrees data set. As you can see, I was mentioning this projection effect is really changing a bit the data, so it is a bit difficult for us. But this kind of data, this stereoscopic data, is interesting because we are trying to reconstruct the magnetic field structure, the three-dimensional magnetic field structure. And for example, if you see that from the Earth viewpoint, that is the HMI or the instrument, we have an inclination of 70 degrees and azimuth of 20 degrees. And if you go 50 degrees to the left, that will mean that we are in the HRT viewpoint. Now the inclination has changed to 80 degrees and the azimuth is 155 degrees. And we are observing to the same point in the sun. So it is important because with this kind of stereoscopic data, we can solve the azimuthal ambiguity that this is what we are working on at the moment. But apart of that, we want also to do some flux study on the evolution of the flux close to the poles. And also we want to relate this magnetic feature in photosphere to other layers like chromosphere or corona using different instruments like EUI or SPICE. And well, that's it from my side. Thanks for your attention.
Okay, thank you very much. All right, so we're going to go ahead and move to the discussion portion of this block. We already have a few questions in the chat, but I think Dean has been very proactive in answering some of them. Just to reiterate, I think we'll start. Yang asked about, from Dean's lightning talk, the radio field BR is measured or converted from line of sight, perhaps the repeat analysis with filling factor solved. I don't know, Yang, did you want to say anything about that? Or Dean, did you want to comment on your answer as to the radial, is the vector radial field?
Yeah, I think Dean already answered the first question.
Okay.
And the second is basically without the filling factor solved, there is a mismatch between line of sight and transverse field. So if you compare the horizontal and the radial, that would have some impact. So currently, HMI has a pipeline product with a filling factor solved. So it would be interesting if apply the same code on this new data product and see what we can get.
Right, was that the, so we were doing this work in HelioCloud. And so if that product was delivered to HelioCloud, we could use it.
So ask Todd.
But we did use the radial field and the horizontal field. We did not in this work use any of the line of sight measurements. We did in earlier versions, but not in this one.
I mean, the vector data, basically we got have the I mean, if you convert to two components, line of sight and the transverse, there is a mismatch if the filling factor not solved.
Okay.
Okay.
Yeah, I believe you.
This is Katie, though. You can do an ad hoc correction to that we should. So
Do you want to expand on that, Katie?
I'll put, well, there is a mismatch. The transverse component is overestimated. But in a paper, Dean, you can do an estimate to correct it and get a better estimate. So I mean, it's not as good as solving the fill factor issue to begin with, but if you're using the HelioCloud data, then I think you could do a correction and get the potential bias out of the HelioCloud data. I'll put a reference in the chat.
I'd appreciate that because we would like to make this useful. So we should be as correct as we can.
Okay, great. The next question came from the chat again. There's a discussion, actually, there's more than a question, there's a discussion about the disambiguation method. I don't know if anybody wants to comment on disambiguation. Please feel free.
I know Dean said that they did whatever HMI does
Right.
for the HMI question.
And then Robert said that HMI provides multiple options for disambiguation. So I don't know, Dean, do you want to clarify further, or anybody else want to comment?
I think Graham's on the line too. I can comment though.
Sure, please.
Or Graham can.
Go ahead.
Okay. So in the pipeline data for the general 7/22, I mean, the areas that have an acceptable signal to noise in the transverse component all over the disk are solved using the minimum energy equation. So even on the poles, if it's got enough signal to noise, in that component, it's using the minimum energy solution. The options come outside of those solutions. So the options are available for the really weak stuff, which we kind of call noise, and so throughout there, for the HMI, there are the conf disambig files, which tell you which pixels used which kind of disambiguation, whether it's the minimum energy optimization or it's one of the three options for the, I'll put air quotes around it, noise pixels. So it's in those noise pixels that we either assign kind of a random disambiguation. Basically, you're saying that we have no information, so we give it a random, or one that agrees with a potential field, or one that best agrees with a radial estimate. Does that help clarify? So if you're in strong polarization areas, you will get the full minimum energy solution.
I think for Dean's work, basically should be the minimum energy solution, because the cutoff is about 100 Gauss, but Dean's the patch basically much greater than 100 Gauss.
The cutoff's it's not a fixed level. The
Right.
cutoff depends on where you are on the disk, and it depends on the orbit. We actually use that noise mask that is calculated as a function of the orbital velocity to calculate the threshold of which pixels are involved in that disambiguation. So it's not a singular cutoff, but that mask is, I try to get everybody to look at that conf disambig, I'll put that in the chat, mask, because that is the one that tells you, yep, these are fully treated, and these have been treated with that quick assignment.
Right, and we did find that, so we have the pixels. Let me do this. We have the pixels that measure where we have the large field, and then Julia went around the edges of those and looked, and the field is dramatically lower outside of regions that were identified as fracular. Now, we didn't check every pixel. I mean, we just accepted that by doing some random checks on a few in the north and a few on the south, that the strong fields were always in the facula. So we are avoiding the noise pixels by only picking the strong field values.
I think again what is considered strong and strong field versus noise, right, varies with a lot of with position on the disk because of the noise, and also with the orbital. So that's where that conf disambig conf disambig dot fits, which is available for the full disk, is a really great tool because it's already identified the ones that are strong enough to be fully treated, if you will.
Yeah, we rely more on the errors, but I will have her. But I know the errors are also kind of funky sometimes. But we will check that.
Thank you. Let's go ahead and move to the next question. Robert, Cameron had his hand raised. Robert, did you have a question?
Yeah, so I just want to quickly ask, can you check any of this using the simulations from MUM simulations or something similar? I mean, in principle, this seems like a question where you could do the board modeling extremely well and see how reliable your results are.
As far as I know, faculae are not measured, and so you don't have this strong field as field concentrations in the models. They tend to be a diffused field, and so you don't have the same. It's not the same situation.
No, I mean, and we reproduce facula really quite well. MUM models, Matthias Rempel, we do, the models certainly contain facula, and they've certainly contained them to the precision at which you put in a uniform polar field or uniform field, you'll get these reversals of the opposite polarity patches. And I would be somewhat surprised if any of the statistics were actually different from those of the sun. And I think that would be a useful check for you. I mean, I don't know where you get the ideas that the simulations don't produce facula.
Well, so the polar faculae are different than the faculae at lower latitudes. So if it does produce faculae, it's probably because it has active regions in the system, and you're looking at the far foot points of the magnetic field from the active regions. The polar faculae don't have an obvious source. They came from some field that was generated years and years ago.
You get polar faculate as soon as or you get faculate as soon as the average field strength exceeds a certain value. This would be the exact situation I think you'd expect from the pole. I would be surprised if the Miriam type models don't do really quite well at polar faculate. I would be somewhat shocked.
Okay.
If it's true, I would certainly be interested because this would be something clearly which would require further work. I would be
Yeah,
surprised.
I had seen there were simulations in regards to things that were associated with active regions, but I can go look at it again with an eye towards isolated fields that have no
Yeah.
obvious.
Yeah, so we do unipolar
uh,
patches, but we do field strengths from 50 Gauss, 100, 200, whatever you think your average polar field is. You can do a simulation, extremely quickly and test it.
Okay, and I'll have HMY team answer their own answer.
I
Todd,
don't understand your, Dean, you say the polar faculae are different from lower latitude faculae. I mean, the
That is
polar
correct.
faculae are basically they're remnants of active regions that are being transported to the poles.
Yes.
And I mean, but of course you shouldn't compare the polar field with the active region field. You want to compare it with the, once the active region is decayed and form the large unipolar regions. Then I would expect the structure, the flux is concentrated in at the supergranular vertices, so it should look the same as the polar field.
The structures may be the same, but the active region faculae have a field line that's coming from a known position on the sun, whereas the polar faculae do not. They're an open field configuration, and so there's a difference in lifetime and a couple other properties that were noticed 100 years ago, and I'm relying on that and also what we've seen in our own measurements of the factor.
Yeah, but the simulations, we have simulations of open, we have simulations of closed. I would be surprised if the properties were different from those of the simulation.
So I'll just mention in the chat, HMI team, which I think is Todd Hoeksema, says Murum won't produce unipolar facula, and Sushant adds on, yes, limited by div.b equals 0 would not allow unipolar patches, right?
What?
that
That's
was
what
my
they say about
understanding.
Murum.
That was my understanding too, but
What?
okay.
Yeah, what? Yeah, so it's a div B, so you can impose a flux. We can have a uniform B initially in our simulation. And it does not violate div B is equal to 0 because it comes from the bottom of the box and goes through the top of the box into open flux, for example. Div B, oh yeah, anyway, I stop.
Okay, I think Todd's gonna comment on that in the chat. So why don't you
Right.
check that out in the chat? Let's go ahead and move to the next question. Amy Asteen, do you see that the polar faculae distribution are off center, i.e. in latitude, longitude location from the rotation axis, or are they aligned with the rotation axis?
So we did that. That was one of our early results, but I would have to go back and check that distribution. I don't have it at hand right now. So I will take that and let her know and let Amy know.
Okay, thanks.
I think we had some problems because we're working at above 70 degrees and we just can't really do a lot of bins. We just are running.
Yeah.
We just don't. We can do like 3 or 4 bins before we become statistically unreliable. So I think we did it once back when Beryl was working on the problem. So I'll go back and see if I can find it.
Okay, thanks. Just interested in it.
Mm-hmm.
Okay. And then next, Nariaki has his hand raised and also had some questions in the chat. So Nariaki, would you like to raise your questions?
Yes, my experience, please correct me if I'm wrong. But if I look at HMI full disk vector data, a polar region is a very small area, right? And to me, most of the areas are kind of noise. And so in terms of disambiguation, I don't know this, the default way it's really applied to polar regions. And and I also compared the HMI and the Hinode SOT data for the polar regions. And I think the Hinode SOT uses basically acute angle disambiguation. If you look at the paper by Ito et al. 2010, and to be consistent with the Hinode SOT, I also use the acute angle disambiguation. It's one of the three options for HMI. And if I do that, to compare the absolute flux with the Hinode, HMI is always higher. And
lots to unpack there, Nariaki. Be careful.
Yeah.
Lots of subtleties there to deal with. Be careful.
I know. I'm not professional at all, so I really rely on somebody like you. But Shudon-san wrote a paper about the assumption of the filling factor, of unity filling factor, makes some bias of the
that yes.
well, do you remember that, transverse and longitudinal components, and so it artificially makes the HMI radial field in the polar region higher. That's my understanding.
Yeah,
And
that's true.
that's discussed in the paper that I cited in the chat.
Yeah,
That's exactly what we were talking about earlier in terms of the potential bias because of that fill factor. And that's what Yang was mentioning in terms of, hey, is there something in the cloud that is because the HMI has a product now for where that fill factor is solved for. And we compared that in the paper that I cited. And so there's a lot to unpack there. So the other thing is that the Hinode data product now, there's a level 2.1 data where again, most of the pixels are disambiguated, and the heliographic, the BR, B5, B theta components are provided. I don't remember, Graham, help me if we're doing the polar data automatically or not. But that level 2.1 data do exist now, and that's using the same algorithm as HMI is using for the disambiguation. So it's not just the acute angle, unless you're again in that really weak signal, basically noise areas.
So
but
I think
true that in the polar region, the most pixels are weak pixels. So only like small patches that have enhanced magnetic field can be properly disambiguated, no?
What weak is relative to the noise, right? So what's weak in this sense in what's disambiguated is different in HMI from Hinode, because Hinode has typically much lower noise levels. So I think you'll find much larger areas of the polar scans are disambiguated in Hinode. I'm not saying all or anything like that, but you'll get some additional stuff there. What I would add though is that I think all of those polar scans have been disambiguated in the level 2.1 data that Kitty was talking about, but there's a whole separate archive of just the polar scans which were inverted with Milos. And I don't think Mark DeRosa's on, but he might be a better person to talk about. I don't know how they've been disambiguated, but I think there's reasons to say that that's a better inversion code to use when you're close to the limb. Kitty, do you know much of that, or do you want to comment on that?
Yeah, because of this, how it treats the scattered light.
Yeah, so if you really want to do the best Hinode polar inversion plus disambiguation, it's probably use the Milos inversion plus some minimum energy. I don't know if those data are public or available, or what the status is though.
Right.
What inversion you said? Milos.
Milos.
Yeah. still Milne Eddington
It's Milne
inversion.
but it has a better.
But the scatter light is treated differently, right? So I know that, yeah. But you have to really look at the IQ-UV component to determine which pixels are really above the noise level.
Yes.
Correct.
Yes, and usually it's a polarization. Usually it's a total polarization threshold that's
Yes.
used.
Yeah.
So.
Well, except for the disambiguation, which specifically looks at the noise in the transverse component, because that's what's relevant for the disambiguation, right? Like the line of sight component is not ambiguous, and so you can have places where you might have a really noisy line of sight, but transverse is still okay. What you do with it is then, be careful. But in terms of where the disambiguation operates in a way that's sort of robust.
So my question is, if this HMI product in the Helio cloud goes through that kind of careful treatment.
Probably not. It's probably just the pipeline data. I don't know, Dean? Todd?
Yes, it's pipeline data.
Okay. I want to, I think we're all caught up with the questions in the chat. There is some additional discussion about this, but I kind of want to circle back to one of the open questions that Anthony raised in his talk. I thought a really interesting question that he posed was, how extreme could polar field variation get? And I think, what he's asking there is in terms of like the polar fields that we measure, for instance, at solar cycle minimum, where they reach their strongest amplitude. It seems that, at least for the last few hundred years, they kind of saturated at some point. Is that kind of your question, Anthony? Is in terms of how extreme can those get, or do you want to elaborate on that question a little bit more?
Yeah, no, I mean, it's not a very, I don't have anything very deep to say, but it's just sort of, as you say, it seems like they haven't varied very much since we've been observing it relatively, but I don't see any reason why they couldn't necessarily.
Well, the WSO fields have changed by a factor of 2. And that would seem to be a large change in the realm of the polar fields. Is extreme more like a factor of 10?
Yeah, that's kind of what I was thinking. I mean, we the largest cycles that we get are, cycle 19 is probably our biggest cycle. And so, 280, that's about number about 280. And so, the fact that we're not getting, cycles that go up to, 300, 400, 500 in amplitude, and is, I think, indication that maybe there is some kind of saturation mechanism in terms of how strong those polar fields can get. And I don't know if that's comes into play in terms of the details of how the dynamo operates, in terms of, is it just a function of how many active regions, can you put out before the toroidal belts reach the equator and the cycle starts to, die down again? Or, is there something else that's maybe preventing the cycles from getting much larger than they actually are, and the polar fields, and by way of the polar fields?
Well, I always thought the polar fields, because they're almost purely advective into the poles, or kind of have a limiting thing, just because basically they get pushed up there. The new field has to remove the old field, and then the new field comes up and gets distributed around the polar cap. And since there's no strongly active dynamo going on up there, you kind of already have a way of limiting it, because the material just comes up and kind of gets into some lattice where they're all kind of spaced the way they want to be, rather than an active region which comes up and the magnetic field is really scrunched together and pushed by quite large velocities around the active region. So, Bob, see, I can, if I say something, Robert will be able to answer.
Yeah, Rob, you want to, Robert, Now you got me fumbling. Robert, you
Yeah.
want to comment, please?
And then so I don't think that's quite the way it works. So on the sun, it's true we have fairly weak polar fields on active region, but on active stars, we have huge spots out there, and this is presumably stuff which has been pushed up by whatever meridian circulation a particular star has. And the whole point is what's
I would disagree with that. The spots, the large star spots, are caused by dynamos acting along the rotation axis and not.
So we can disagree on that point, but in any case, the amount of facts you have to get to the pole is how much crosses the pole. And as we said, this is one active region. So you can imagine a not very often occurring case where you have 10 large active regions occurring near the end of a cycle across the equator, so highly tilted across the equator. If those are like we expect, most of the polarities of each of those 10 active regions will be carried by the meridian flow to the pole. And it will eventually arrive at the pole, and it will have a polar field which is 10 times stronger than we have at the moment. This doesn't happen very often because you need 10 active regions occurring relatively late in the cycle, very highly tilted and across the equator. But there's nothing in principle, so far I can see, which would then prevent that flux just being advected to the poles.
But you also have to, I think, have a very specific kind of scenario going on with in terms of the dynamo, right? Because I think part of the quenching that occurs at the end of the cycle is associated with the toroidal belts coming together, right? Which are going to reduce the field there. And so you'd have to have some kind of asymmetry that would allow those toroidal belts to be separated by enough distance that you could create large active regions at the equator.
I don't think so. So you consider the last 10 active regions of a cycle. They're all going to occur fairly close to the equator. And if they're all orientated completely north-south, then most of the flux, the active regions will end up in the opposite hemispheres. And instead of having the polar field of one polar fields of the strength of one active region, you'll now have polar fields which are 10 active regions, purely by chance. What happens afterwards is more complicated. There's nonlinearities and so on. But I don't think we've got any reason to believe that flux wouldn't be advected somewhere up towards the pole.
No, I agree with you. My comment was more that those active regions at the end of the cycle tend to be fairly weak, and so their contribution to the dipole, even though they
it depends how close we get. I just imagine
most of they have a small tilt. The active regions at the end, near the end of the cycle, have small tilts, so they're not going to contribute much.
Typically, but
not
it's large random scatter.
Right.
And randomly you can get, of course, it doesn't happen at all. 10 of them all orientated in the same way is very low probability. This is why we don't see it. In principle, you can imagine it.
Yeah, I think that's a very, very interesting thought experiment there. Lariaki, I think your hand was next in terms of questions in the chat, and then I think Sushant after that.
No, actually, it's not really chat related, but people talk about the importance of polar missions to discover something. But without those missions, can we safely say that there is nothing like active regions in the polar region based on the existing data? Can we safely say that?
In terms of emerging strong,
no, in terms of
very
magnetic field
concentrated
strength, there's no such thing as top-notch distribution of magnetic field that Anthony talked about, from Life's results before. Top-notch distribution, magnetic field getting stronger at the pole. There's no such thing, or no active regions with sunspots in the polar region. Is that a correct statement?
I think active regions. Go ahead.
Because you would see them. they're obvious against the limb. They'd have to be at a very advantageous place and time to have escaped detection for the 150 years people have been looking at solar images.
Yeah, we could have observed it if there was such thing.
But I think you're mixing up two things here. There's no active regions there at the poles. This is, I think, sure, 100%. But this isn't the same as the field's not concentrated there. But it's concentrated to average field strengths of 10, 20 Gauss, which is reasonably stronger than, for example, at lower latitudes during solar minima.
Right, right.
But distribute to small patches, not in a big.
Right. The average field is not completely reflective of the actual field that's in the patches. The field has concentrations that when you make a broader view like WSO, it encompasses many of those patches.
Okay. And then
But I would like to point out that from 1874 to about 1925, the British Astronomical Society did watch the poles of the sun a lot, looking for things, because people assumed that there was nothing there, but there was actually a paper that they talked about the faculae and looking for things in the poles. So that's about 50 years of their white light photography, and probably enhanced by some others as time went on. And they appear to have stopped their polar emphasis in 1923 because they hadn't seen anything. So I think that people had looked for active regions in the sun a lot in the past, and they just stopped because they hadn't found it.
all right, Sushant, do you want to ask your question?
Yeah, I wanted to comment on the previous discussion on what could limit polar field buildup. And there are two mechanisms that I can think of. The polar area is kind of small. It's not that large an extent, the area above 70 degrees latitude. And if you build up enough polar flux, there would be a diffusion pressure in that area. Magnetic field would try to diffuse, and that would resist building up more polar flux. The other thing is we do see an anti-correlation of the meridional flow at mid-latitudes as a function of the strength of the solar cycle. The stronger solar cycle, the slower the meridional flow. So that itself is a resistive mechanism to transporting more flux towards the poles. And there has to be a saturation mechanism, right? Otherwise, you would have an instability. Like the stronger polar flux, stronger cycle, it would be an infinite lunge.
Have you actually observed that? Anti-correlation between the.
Yes, I believe it's been modeled as well.
I mean, that's what I put in my own models, but I don't think it's actually been observed. Or you're saying it's been observed?
We have, at least for the last two solar cycles, we have good measurements of that. So solar cycle 23, there was a much larger slowdown of meridional flow compared to cycle 24. Right. In cycle 24, it was more or less constant. There was a very slight slowdown of meridional flow, but during cycle 23, it slowed down by about 4 to 5 meters per second.
And another thing about as the new cycle is headed up into the poles, so I've thought more about the pre-reversal evolution than the post-reversal. A lot of the flux cancellation occurs across the polar crown filament. And so that's a dynamical process that also limits the ability of the new flux to get into the pole and prevents so one thing would be that as the new flux is moving up, the new cycle flux, it could compress the old cycle flux and actually increase the unipolar field near the pole until it finally is able to get rid of it. But what really happens is the polar crown filament sits well away from the pole, and the new cycle kind of wipes out the old cycle as a function of time. And so the new cycle is more gradually destroyed, or the old cycle is more gradually destroyed. And then the polar crown filament fades as the flux that it contains gets smaller and smaller. So there is a dynamical process that limits things on the rising phase of the cycle. And I hadn't really thought about what's happening on the declining phase.
All right, so this has been a very interesting discussion, but we have reached the end of our time for this time block. So I'm going to go ahead and start the lunch break, the second lunch break now. But I do encourage you, there's still more discussion going on in the chat and on Slack. If you want to keep talking during the lunch break, you are more than welcome to continue doing so. And then we will reconvene in 30 minutes for the final block of our workshop today. Thank you once again for all of our speakers, our scene setters, and everyone who contributed to the discussion. As I said, feel free to continue the conversation, and then we will officially reconvene in 30 minutes. Thank you.